Hello friends, welcome to our channel. In this video, we would analyze the heat transfer from a rotating body by using the sliding mesh approach in ANSYS Fluent. Before starting the tutorial, let's briefly know about the sliding mesh approach. There are generally two types of methods mostly used to simulate a moving part inside a flow domain without changing the mesh. The first one is the moving reference frame, and the second one is the sliding mesh approach. The moving reference frame approach, in short, is also called the MRF approach, in which the parts do not move. It's a steady-state analysis. So, here is the question comes, how in MRF parts don't move, but do we get the rotation results? The answer is local acceleration terms. The local acceleration terms are added as source terms to each grid cell to account for the motion of the parts. Though this approach provides the solution at a faster rate than the sliding mesh approach, it has certain limitations. The results are not so good and not accurate in most of the cases. So here comes the second approach, which is the sliding mesh approach. In the sliding mesh approach, we use the transient solver, in which the parts are actually moving. It gives a better and more accurate result than the MRF approach. In both cases, we need the non-conformal mesh. In non-conformal meshing, the mesh of two cell zones is not connected with each other. Here the question comes, if there would be no connection between the cell zones, then how the solution would pass in between the zones? The answer is that after creating the non-conformal mesh, we need to set up the mesh interface. So the solution interpolation can occur at these interfaces. So the flow result can pass through this. So, let's see how we could set up a sliding mesh problem using ANSYS Fluent Solver. For this demonstration, we had taken a problem. There is a rectangular channel section, which surface temperature is 310 K. It is rotating at an angular speed of 5 radians per second. It's kept inside a rectangular tunnel in which there is airflow of 1 meter per second. Find out the variations in the flow pattern and heat transfer from the plate. From this demonstration, you would learn how to create a 2D geometry for sliding mesh problem, how to create a non-conformal mesh, how to provide named selection in meshing for sliding mesh problem, set up the solver for a rotating domain, how to record the solution animation. Before we start the geometry creation, first single-click on Geometry, then in the right side window menu select Analysis Type as 2D. After that, you need to right-click on Geometry and select the second option, which is ANSYS Design Modeler. In this, first set the units of the geometry to millimeters. Select the XY plane and click on Z to make the sketch normal to the screen. Now go to the Draw toolbar and select the Rectangle tool. Draw a rectangle in such a way that the center should be nearer to the origin. Now go to the Dimensions toolbar and put dimensions to all the lines. Click on Constraints and select Symmetry. First click on the axis, then the two lines on both sides of the axis. Now, these two lines are symmetric about the axis. Similarly, for the horizontal sides, select the x-axis line and the two lines on both sides. Now the sketch is fully constrained. Now we need to put the actual dimensions to the sketch. We would convert this 2D sketch into the 2D surface body. For this, go to the Concept menu and select Surface from Sketches. Select the sketch and click on Apply. Change the operation to Add Frozen. Click on Generate. This is the geometry for the outer fluid domain. Now create another sketch for the inner rotating body. In the new sketch, draw a circle with a center at the origin and a rectangle at the middle. Put the symmetry constraints on the sides of the rectangle. Put the dimensions. Again, go to the concept menu and select Surface from Sketches. Select the new sketch and click on Apply. Select the operation as Add Frozen. Then click on Generate. Now, we can see two surface bodies, but there is an overlap. So for this, we need to do the Boolean operation. For this, go to Create menu and select Boolean. Select the operation as Subtract. Select the larger surface body as the target and the smaller one as the tool body. Use this selection tool to select the smaller surface body. Then in Preserve Tool Bodies option, select Yes, as we need both surface bodies. Click on Generate. Now we can see all the surface bodies are unique and there is no overlapping. As we do not need the inner rectangular part, so suppress this. Close the geometry and proceed for meshing. At first, generate the default mesh. Click on Mesh, then go to the details of the mesh table. Enable the adaptive sizing option. Enter the resolution as 7. Now go to the meshing, right-click, and insert face meshing. Select the outer face and click on Apply. Similarly, insert the face sizing for the inner surface. Now we can see there are some void spaces at the interface. So we need to create more cells here so that there would not be many void spaces. For this, select the circular edge and insert edge sizing to it. Select the type as number of divisions. Enter the number of divisions as 360. Change the behavior to hard. Then click on Generate. Now we can see there is no void spaces at the interfaces. Now we would provide name selections to the boundary surfaces. For this, select the Edge Selection tool. Select one edge of the outer geometry and right-click. Name it as the inlet. Similarly, select the opposite end and name it as outlet. Using the face selection tool, select the outer face and name it as fluid zone outer. Similarly, select the inner one and name it as fluid zone inner. Select the edges of the inner rectangle and name it as plate wall. You can check the number of elements or nodes in the mesh statistics. Right-click on Mesh and click on Update. This would link the mesh to the ANSYS Fluent CFD solver. Close the meshing and open the setup. Select the double precision and click on Start. Select the transient solver. Check the mesh and make sure that there is no negative volume present. Go to Models and turn on the energy equation for heat transfer calculations. Select the K-epsilon turbulence model with standard wall function for flow calculations. Keep the default material as air. Go to the cell zone conditions. Open the inner cell zone. We would put the rotation to this zone. Enable the mesh motion option. Enter the rotational speed of 5 radians per second. Relative to cell zone is absolute. Then click on OK. Keep the default settings in the second zone, which is the outer fluid zone. Now go to the mesh interface. Delete the default mesh interface and create a new one. Click on Manual Create. Put the name of the new mesh interface. Select the source and target contact. Click on Create. Close it. Select the mesh interface and click on Close. Now go to the boundary conditions. Group the boundaries as per their zone types. Open the inlet boundary. Enter the inlet air velocity as 1 meter per second. Switch to the Thermal tab and put the temperature of inlet air. Keep the default turbulence inputs. Click on OK. Keep the default pressure outlet boundary conditions for the outlet. Open the plate wall boundary. Enable the moving wall option. It would properly account for the wall shear. Since the motion has been set in the cell zone, we will simply tell the boundary condition to use the same conditions. That is zero velocity with respect to the adjacent cell zone. Switch to the Thermal tab and enter the wall temperature of 310 K. Then click on OK. Open the surface body, which is the outer wall of the outer fluid domain. Keep the wall as adiabatic. So put the heat flux as 0. Close the boundary conditions. Go to Solution Methods. Select the scheme as coupled. Set the gradient as green Gauss cell based. Second order upwind for turbulence kinetic energy and turbulence dissipation rate. Now go to Initialization. Select Hybrid Initialization and click on Initialize. Open the calculation activities. Click on Solution Animations. Name it as Velocity Animation. Now we would create a new contour. For this, click on New Object. Select Contour. Select Contours of Velocity. Click on the Save display. Set the second window to observe the velocity contour variation. Similarly, create another animation for temperature variations. Set the third window for temperature variations animation. Now go to Calculation Activities and select the Auto Save option to save the results for each time step. Go to Run Calculations, enter the number of time steps and time step size. I want to simulate for 6 seconds, for which I had taken the number of time steps as 600 and time step size as 0.01 seconds. Click on Calculate to start the iterations. The calculation is complete. Now go to Results and click on Animations. Playback. Select the velocity animation and click on Play. Here you can see the airflow velocity variations within these 6 seconds. Similarly, check the temperature changes. Save the solution and proceed for CFD post-processing results. Open the time step selector. Select the first time step. Click on Apply. Go to Insert and insert a new contour. Select Velocity as the variable. In the location, select the symmetry plane in Fluid Zone 1 and Fluid Zone 2. Enter the number of contours as 100 for more smooth colors. Then click on Apply. You can also change the default legend view from Scientific to General. Click on the animation. Select the location where you want the animation file to be generated. Click on the option and set the video resolution and sizes. Click on the play button to start creating the animation video file. This is the output file generated. This is the velocity variations in the flow domain. Similarly, create the temperature contour and record the animation. This is the output of the temperature changes animation. Go insert and make a new streamline. Turn on the wireframe to observe the rotating geometry properly. Similarly, record the animation in another file. With this, we conclude the demonstration. Hope you have liked this tutorial. Please subscribe to our channel. Comment for any suggestions or queries. Keep learning and keep sharing. Thank you.